Howdy, people. I'm going to do one solved example here for you about this is a standing wave on a string. You'll also be responsible, or you are also responsible for standing waves in air columns. I find those to be a little bit easier as they skip one of the steps that we'll have to go through in this problem. So, the basic steps are going to involve the following. First, you got to make a drawing of what's going on. In this case, the system that's oscillating, well, this is a string. All right, so all I do for a string is do that. There's the string. All right, if it's an air column, if it's a tube that's open on both ends, you do that. If it's a tube that's open on one end and closed on the other, you do that. Right, so you draw the system. So I'll say drawing, and here we want system and standing wave. All right, so string, yeah. Fix them both. Tension. Now check this out. Oh wait. At some point, this question did say that this thing's vibrating in the third harmonic. All right. So what I might do if I were you is say, let's draw the fundamental vibration first. Here's the fundamental. Right? The fundamental, we say L, the length of this thing, that's half a wavelength. You need to recognize that that's half a wavelength. There'd be the whole wave, right? So we see on that system, on that string, half of a wave. All right, now, if we say the third harmonic, what that means for us is we say that L is 3 half wavelengths. In our system, the mode of vibration, they call it, or the standing wave, looks like this. Instead of 1 half wavelength on that string, whoops, there's 3. You've heard me say it might be easier to draw the wave first and then draw the string. All right, so that's what we're saying. We need to use this for the third harmonic. L is 3 halves of a wavelength. Okay, so this is our big step 2, is this stuff. And what I mean by that, this stuff is equation relating L and lambda. Right? There it is. L is 3 halves of a wavelength. Okay? Step 3 is going to be using V equals F lambda. Now, depending on the situation, sort of situation 1, if we're in air, this is an air column, V is just somewhere around 340 meters per second, the speed of sound in air. Might be 343, might be 330, somewhere around there. That's, the range of typical speeds of sound in air. All right. In the other case, where this is a wave on a string, the likely scenario is that you're going to use V is T over M over L, square root of T over M over L. All right, so there's that extra step in some of these, well, in the string problems where you have to sometimes typically find the speed of the wave. All right, so let's see, what's the vibration frequency? So notice I haven't really even looked much at what the question asks yet. I needed that third harmonic thing to do this, but we're looking for the vibration frequency. So that means we're going to use this, and we're going to say that frequency is V over lambda. Well, how do we find V? Well, we're going to do this stuff to find V. How do we find lambda? Well, we're going to do this stuff to find lambda. All right, so let's see, V is the square root of T. Now I'm going to write it like this. A lot of people will write it like that, where mu is by definition M over L, which is 0.040 kilograms. Yeah, let's move that. Oh, come on, will you? 0.040 kilograms, and the length 8 meters. Wow, that's a pretty long string. And So if you want, that gives us mu is 0.005 by my math, and a couple of zeros for the right sig figs, kilograms per meter, right? I mean, am I right or am I right? Yeah, I'm right. So, yeah, duh. So, okay, there's mu. Now, V is the square root of T, 49 newtons, over mu, 0.005 kilograms per meter. Now, do you have to do separate steps to find mu? And then, I mean, could you just, if you want, do it all at once and use the V is T over M over L? Absolutely. Absolutely. I just want to show you that this is a way you see it a lot. Okay. All right, so square root of, we need 49 divided by 0.005. That's that, 9,800 square root of that. So the speed of this wave is 99.0 actually meters per second. Okay, so there's takes care of that. For lambda, we're going to have to do, well, if L is 3/2 lambda, and that means that lambda is 2/3 of L. So 2/3 of 8, 5.33 meters. And then finally, you put those back into F is V over lambda, 99 over 5.33. And that gives us our 18.6 hertz. All right, so sure, everyone gets that, 99 divided by 5.33 is 18.6, sure, but the much more important stuff is, the only way we get there, I think, is by making sure we can handle what's going on here. This is a string. We know there's a node at both ends, so we should draw. I recommend drawing the fundamental, and then, okay, so this is our harmonic, the third one, so we do 3 times the fundamental wavelength there. Right, that gives us this equation that relates L and lambda. Right, it's an absolute must. And we're doing this, sure, and for some situations like the string stuff, we have to go the extra step of calculating what V is. All right. Now, will every problem be, here's a situation, find the frequency? Absolutely not. But you're going to do these 3 steps. It's going to probably include a drawing. It's going to include relating L and lambda for sure, and it's going to involve V equals F lambda for sure. Okay? So, yeah, we'll quiz on for sure. Next time I see you guys, be ready for a quiz that involves one standing wave on a string and one standing wave in some sort of air column, whether it's open on both ends or only open on one. Okay, folks, I bid you farewell.